Hello, everyone, and welcome to the NAE Grand Challenges for Engineers podcast. I am Marlene Orozco, and I am here with my group members,
Charles Tian,
Omer Kamran,
David Arts Hussein.
Li Tao Xiao,
and we have decided to choose the Providing Access to Clean Water Challenge. According to the Grand Challenges for Engineering, lack of clean water is responsible for more deaths in the world than war, and about 1 out of every 6 people living today do not have access to clean water. And more than double that number lack basic sanitation for which water is needed. In some countries, half the population does not have access to safe drinking water and hence is afflicted with poor health. Our team has decided to develop a code that will allow the user to view the urban and rural improvements of potable water for each country based on the data we have gathered. The motivation and background for our project is, since one of the most basic needs for humans to survive is clean water, yet some countries are struggling to survive because they do not have access to it. Some challenges include cost of purification, lack of technology, contamination, and demographic changes. For this challenge, our goal is to develop a code that will allow the user to determine if the country selected needs to implement technology for access to clean water. Engineers can easily use our code to decide which country needs advanced technology and use problem-solving skills that can remove contaminants from water and help distribute to countries that need access to clean water. Now I'm going to pass it over to Devin.
For our proposed algorithm, our first step was to load in the data set for each country for the urban, rural, and the total potable water that's within each country. And in our code, this is shown by line 11, where we use the function xlsread, and in the parentheses is the name of our data file, of the Excel file, and we have it saved to these 3 different variables. And then this second part from lines 13 through 16 is basically separating all the data into using the appropriate indexes for the data, because when we loaded it into each of the 3 different variables, the data, some of the variables had certain items missing from our data set, so we wanted to do this to help us concatenate the data together at the end. And then we did that until we were able to put it into a final matrix called final, as you can see from lines 23 to 26, as well as 22, which was basically concatenating our converted data set indexes from the numeric data type to the cell data type. And for our second step on our proposed algorithm, we decided that we were going to find and delete data for countries which have a hyphen or an NAE within the data set. And we did that right here from lines 75 through 89, and we were basically we converted all the data back to a string earlier in the code, around lines 31 through 35, and we used the for loop to do a string compare statement to find where the hyphens as well as the NAs were in the data. And then our data had been split up between the years, the countries, as well as the data for the rural, urban, and total drinking water percentages. And then, so we basically used the function. We changed the data that had the hyphen and the NA to blank cells. So we used the function is missing of that array where all our data is saved to find where there's blank spaces, and we did basically if the row is missing, to delete the entire country's data, as it wouldn't have any use to our project. And then for step 3, we decided that we were gonna create a menu that allowed the user to select a country and output the data, and that was shown here, where the user was given an option from the menu to select a country using from the names of our countries. So our algorithm, it was efficient because it graphs all the data for the urban, rural, and total drinking water in the user's selected country, with the average showing the total average for all the countries combined of the percentages of drinking water, which allows for comparisons, which is effective because it's easily usable for by the user, and helps our problem, because our problem was that we wanted to help to remove contaminants and as well as help see which countries were below or above average, to see which countries need help in having better access to clean water. So now Umer will continue.
Okay, so after the user has selected the menu and the country has been saved, okay, and then we're gonna use the mean and min functions to analyze our data and calculate the minimum and average percent of the potable water in those areas, as well as the total. And then we're gonna output those numbers using fprintf in the command window, and after the calculation, store all the new data in a vector and export that to a file. And then once a user has selected the country, it'll display the bar graph for that country, which shows. Okay, so now I'm going to run the code. So when you run the code, the menu shows up for all the countries. So for the first one, we're going to choose Angola. And when you choose Angola, it shows the bar graph, which and it's split up in 2 years, 1990 and 2015. So in 1990, it shows the total improved percentage of clean water or potable water in urban areas, rural areas, and the total. And it does the same for the year 2015. And this line right here shows the average percentage of potable water in all countries. So as you can see from this chart, Angola is below average in their percentage of potable water. So after the user selects one country, a menu option comes up that says, would you like to check another country, which we had using a while loop. So we click yes, and the menu comes back up, allowing the user to select a country again. So for this one, we're going to choose Japan. After choosing Japan, it shows a new graph. And this new graph for Japan has all the percentages for like the same thing, 1990 and 2015. And in this one, you can see how Japan is above average in their percentage of potable water. So you click no, and when you click no, it ends the code. Okay, so now I'm going to give it over to Li Tao, and he's going to explain the outputs.
Okay, I'm talking about the command window of the minimum and average the minimum of the urban area, the country is Cambodia. And the minimum of the rural, the area of countries of Ethiopia. And the minimum of the total area is Ethiopia too. And the average of the urban area of all the country is about 93%, and the average percent the water of the rural is about 77%, and the average percentage of the total country is about 83%. Now I'm passing to Charles. He going to the conclusion.
Everything has two sides. Our coding has its limitation and applicability. From the original data, we can see there are some missing data. In addition, the year in this data is old. This leads us to less accurate. So every time the user want to use our code, have to update the most recent data. If user picks some countries and our code doesn't work, that means we don't have enough data to show the graph or the output. The possibility of our coding is when engineers want to get started helping an area improve its water resource. First, we can use our code to see if the area needs our help. Then we can find out corresponding area with high water improve and learn their technology or method. We can even find the area that needs most help. Our code is allowed engineers to have a better focus on those areas that need to help.
That is the end of our podcast. We hoped you enjoyed it, and thank you for listening.